Hello there, and in this video we're going to discuss another application of integration. It's sort of related to solids of revolution, but in this case we're not going to be revolving curves around an axis. Instead, we're going to be using functions to dictate a particular dimension of the solid, and we're going to be using special cross sections of that solid to sort of generate the volume or surface area if we're interested in finding that. So, for example, consider the curve y is equal to the square root of x. So I'm going to be looking at this from a particular angle. So I'm going to be looking at this as the x-axis, and I'm going to be looking at this as the y-axis. So the z-axis, let us assume, is going to be going in this direction. Actually, let that be the z-axis and let that be the y-axis. So the curve y is equal to the square root of x is going to be this curve right here. So this is y is equal to the square root of x. So if we look at its mirror image over here, this curve right here would be y is equal to negative square root of x. So what I'm going to do to sort of generate this solid is I'm going to consider a triangle whose base is the distance from negative square root of x to the square root of x, and I'm going to make a triangle from those vertices. So let's assume that this is an equilateral triangle. So that would be one triangle that's part of the solid. So another one would be here. So that would be another equilateral triangle. So if we sort of go out more, we would have this triangle. And if we were to go out even more, then we would have that triangle. And we could consider, say, another point here. So we have that triangle. So if we consider all these triangles together in a continuum fashion, then that would generate a solid. And let's assume that we're going to end this solid, start off at x is equal to 0, and let's go all the way out to the point x is equal to 9. We'll choose a pretty number so we can take square roots of it to get pretty answers. So I'm going to look at a cross section, namely directly at the x-axis. So what will that look like? So I'm going to be looking at this from this perspective. So let this be the y-axis, let this be the z-axis, and let the x-axis be coming directly out at us. So if we look at the red triangle, for example, so there's vertex 1, there's vertex 2, there's vertex 3. So let's find the area of this triangle. Okay, so the height, or the distance from this point to this point is the same as the distance from this point to that point. So these distances here represent the same exact thing. So this point right here is going to be the square root of x. So that's the distance from here to here, which means the distance from here to here also should be the square root of x as well. So we have the square root of x there, we have the square root of x there, which means the total distance here is going to be 2 square roots of x. We're assuming that this is an equilateral triangle, so that means what? So that means each of these side lengths are also going to be the 2 square roots of x, but that part is not actually necessary. So what I want to do is find the area of this triangle. So note that the area is going to be equal to 1/2 the base times the height. So how can we find the height of that triangle? So we can look at only one of those pieces. So this is going to be square root of x, this is going to be 2 square roots of x, and we want to know the height. So we know by Pythagorean Theorem, the square root of x squared plus h squared must be equal to 2 square root of x squared. So square root of x squared is just going to be equal to x, plus h squared is going to be equal to 4x. So it means h must be equal to 3x, which means that h is the square root of 3x. So if that is the height, then the area for any one of those triangles is going to be 1/2, so the base is going to be 2 square roots of x, and the height is going to be the square root of 3 times the square root of x. So we can do some simplifications here. 1/2 will cancel, which is nice. Square root of x times the square root of x is just going to be equal to x. So therefore the area formula is going to be equal to root 3x. And that's going to be true for all x in the interval 0 to 9. So now I can look at the solid and add up all of those areas, which are generated by this area formula. So we know that the volume of the solid is going to be equal to the integral of the areas, which from this is going to be the integral from 0 to 9 of this area function, which is the square root of 3 times x dx. So we know that that's going to be equal to the square root of 3 over 2 times x squared, evaluated from x is equal to 9 to x is equal to 0. 9 does not generate, 0 does not generate anything, so we just plug in 9. So we have 81 square roots of 3 over 2. And since this is the volume, this is going to be cubic units. And that's going to be the volume of that region. So let's consider the same exact type of shape. So let's consider this again. Let this be x-axis, let this be the y-axis, let this be the z-axis. Let's consider the same exact curve. So y is equal to the square root of x, and its mirror image, negative square root of x. And instead of doing equilateral triangles, we can do another shape. Why not do a square? Right, so let's assume this is a square. So that would be one square. That would be another square. That would be another square. That would be another square. And you should be able to see the solid that would be generated. And again, we'll go from, say, x is equal to 0 to x is equal to 9, and sum up all of those squares up to get some volume. All right, so let's look at one of these squares. So this is going to be the z-axis, this is going to be the y-axis, and the x-axis is going to be looking at us directly. So let's look at the rid rectangle, for example. So here's our square. So we know that this distance is going to be the square root of x. This distance must be the square root of x. So if that is the case, then that means the entire length of the square is going to be 2 square roots of x, forcing the height to also be 2 square roots of x. So if we want the area of that square, we know that's length times width. So that's going to be 2 square roots of x times 2 square roots of x, which is going to just be 4x. So we want to integrate all those areas from x is equal to 0 to x is equal to 9 in order to generate the volume of that solid that would be generated from this cross sections. So volume again is going to be the integrals of all the areas of squares. So that means the volume is going to be equal to the integral from 0 to 9 of 4x with respect to x. So by the fundamental theorem of calculus, we know that that is equal to, so x squared divided by 2, so the 2 and 4 will simplify. So we're just going to be left with 2x squared evaluated from x is equal to 9 to x is equal to 0. As usual, 0 does not contribute anything, so we just plug in 9. So we have v is equal to 2 times 9 squared. 9 squared is 81, and 81 times 2 is going to be 162. So we have 162 cubic units for that particular volume. And this is how you can find the volume of solids if you want a particular cross-sectional area. And you can also find the surface areas of these things, similar to how we did the surface areas in the previous videos, by finding the integrals of circumferences or perimeters of the objects if you're able to figure them out.